problem 11-13 is a circuit problem with a battery, 2 resistors, and an inductor. Alright, so part A asks you to determine the current immediately after the switch is closed. So that's when the switch closes to A. So the current will start out from the battery, travel through this resistor, travel through this resistor, travel through this inductor, and all the way back to the battery again. Well, so immediately after the switch is closed, the resistance of the inductor is infinity because the inductor is resistant to any kind of change. So for part A, the answer is 0. There's no current at all after the switch is immediately closed. Part B asks you to determine the current after a long time when a steady state situation has been reached. So when the switch has been closed for a long time, when steady state is reached, the resistance of the inductor is 0. So you're only concerned about these two resistors right here. So the equation you would use is V equals IR. The only source of voltage in this circuit would be the battery, so with an EMF of 50 volts. So 50 volts equals I, which is trying to find, then R, 100 ohms, plus 150 ohms. Right, and simplify that, you get 250 volts equals I times 250 ohms. Move this over here, you get I equals 1/5 amps. You could also write in decimal form as 0.2 amps. Right? Part C asks you to sketch a graph of current versus time after the switch is closed. So this will be 0. This axis shall be current. This axis shall be time. So we know that immediately after the switch is closed, the current is 0. But after that, it begins to grow at an exponential decay, reaching an asymptote over here. This asymptote represents the ideal steady state, which should give you a current of 0.2 amps, but you don't need that part for now. Okay, so part D asks you to determine the energy stored in inductor L when steady state has been reached. So from the equation sheet, you can see that the potential energy of inductor is given by 1/2 Li squared. So immediately after the switch is changed, the current will still be 0.2 amps because that is when steady state has been reached. So you have to do 1/2, what is this, times 0.2 squared, yes? Okay, so cross this out since it's just 1, and I'll just write these in fractions since fractions are easier for me. Alright. Joules, of course, because that's for potential energy. So this is your answer right here, and you can also convert decimal form, which is 0.02 joules. So that's part D. Part E asks you to determine the current in the inductor immediately after the position of the switch is changed. Well, the inductor over here is resistant to any kind of sudden current changes, so the current will stay the same because it's very hard to make the current inductor change. So immediately after, it'll still be the same as right before the switch is closed, which was determined in part E to be 0.2 amps. So that's your answer, part E. Part F asks you to determine the potential difference, or the V, across the inductor immediately after the position of the switch is changed. So for this one, you would use Kirchhoff's loop rule. Kirchhoff's loop rule. You're only concerned with this part of the circuit because when it's part B, this part just falls inactive, and the inductor still has some V left. So this acts as a battery and powers this part of the circuit. So Kirchhoff's loop rule dictates that the net V throughout the circuit will be 0. So so as determined in part E, the current in the circuit immediately, in this part of the circuit, immediately after the switch is moved to B, is still 0.2 amps. So you would use V equals IR to find out the current dissipated, to find the voltage dissipated in this part of the resistor. So to use V of the 150 ohm resistor equals 0.2 amps times 150 ohms should give you 30 volts. So by Kirchhoff's loop rule, since this thing dissipates 30 volts, this thing must provide 30 volts. So the EMF of this thing is 30 volts. So that would be your answer, part F. Part G, the last part, asks what happens to the energy stored in inductor as calculated in part D above. Energy in the inductor eventually dissipates away through forms of, because of resistance. And as you know, when some resistance provides a form of friction from the small electrons inside the inductor, so it is dissipated as a form of heat. And that is how you do problem 1113.